Hello everyone. This is a short update on the continuing saga of the quad block monoblock amp project. Just wanted to go over some progress. I haven't really been working on this for a while. Just other things taking precedence in my life and my work right now. So I felt that I should probably just maybe release a 20-minute video and kind of just discuss what we have so far in terms of the project, what's being done, and remaining steps in the project. So just to recap, we were planning on having an old style vacuum tube amplifier, what's referred to as a monoblock, with 4 tubes running in a push-pull configuration, 2 per side, relatively small wattage output, say 12 to 15 watts, using 6AQ5 tubes, which are commonly used in the day in televisions as an output amplifier for the audio. So in the time that since I've done the last video, I've done a couple of things. I've advanced quite a bit in going back to the original diagram. Most of the parts, or the physical manifestation, I guess you could say, of the modules, the sub-blocks, have been done. Let's start maybe with the high voltage power supply here. That is going to be this module here. Now what this is a aluminum backplate that I put a couple of terminal strips on, and I've actually used these studs, threaded studs, as a mounting point for the transformers that go on top of the chassis. So in understanding what this is and where it goes, this would be the I believe this is the larger power transformer. So if you look at this, for example, you can see where the transformer holes will need to be for the wiring, and this translates to, let's see if I can lay this out. That would translate roughly to something like that. So this would be in the chassis in the bottom, and not tied down or anything, it's just loosely floating around, and it'll act as the anchor point for the transformers on top, as well as a little bit of support for the top of the box. This is not aluminum, this is mild steel, but even so, the transformers are pretty heavy, so this acts as a little bit of an assist to prevent the top from deforming and moving around. And you know, if you were to ever ship this or something like that, there is the danger of an impact on the box causing a transformer to bend and possibly deform the top of the box. So, I mean, there's a number of reasons why I chose it to do this way. It's modular, which is a nice thing, because I can, at the end, when I've got all of the subcomponents done, I can just wire it all together without having been in the box, and I can get it all up and running and debugged that way. That way I don't risk, you know, potentially drilling the wrong holes in the box and screwing something up. So before I do this layout, I like to kind of sketch it out. So I'll do a diagram, something like this. I know this was a first attempt here. So I'll kind of lay out where I want the components. This is kind of useful for terminal strip designs, because you only have so many points on a terminal strip, and you have to kind of plan out in ahead where all the point-to-point wiring is going to be going on those, to make sure you don't run out of terminal strip points. And so you can see from the diagram, it pretty much matches the layout here. Let's see if I get this in shot. So that's the the high voltage power supply. I haven't powered it up yet, but I don't think there'll be a problem with it. It's a pretty simple design. Up next, we have the tube point-to-point wiring system. And for that, I designed a second aluminum chassis. This has a couple of benefits to it. As I said before, I can wire this up. It hasn't been wired up yet, but I put the ground bus in. And I can power it up and hook it up to all the other modules, so that I can have it live and running on the bench without actually having it in the chassis. So I can test things out and make sure they're working. And then as a last step, I just put it all in the box and it's finished. The other thing I like about this design is it neatens up the surface of the box, because you don't have a lot of holes in the box with a lot of hardware poking up through for the sockets, for example, and sort of making it a little bit busy on the top. Instead, what happens is I use a Greenlee punch, and I'll punch out the holes for the tubes a little bit oversized, and then this goes into the bottom of the box, something like that, and then screws into the side. So you can see here I've got the side bracket height noted here, so I can actually figure out where to drill 2 holes for mounting this into the side of the box, and then threading this bracket here to hold it in. Let's see if I can keep this in the shot. Then the outside of the box, I'll just use some 1/4 inch or 3/16 wood to create a wooden box outline for this, and some nice wood, some hardwood, and I'll use that to finish off the box itself. This green stuff on here, by the way, is just painter's tape. I just use this to do all the hole layout, and once I've punched all the holes, I'll just take the tape off, and that keeps the paint job on the box nice and clean, because the box has been pre-painted, and it's a bit of a japanned or a look, which is a kind of like an orange peel style. It's a term used in the paint job done on some boxes, some older equipment. You see some old transformers that also have that japanned look. So that's the tube plate, and I'll get to that, wiring that up next. As with the high voltage power supply, you want to have a good idea of what goes where in the point-to-point wiring. This looks a little busy. Maybe it might be better to lay it out that way. But this gives me a good idea of where all the components are going to go, to which terminal lug. And I'm pretty confident at this point that I'm not going to run out of terminal points in the diagram. Something that's a little hard to see here, this is where the filament voltage comes in. This circuit is all 6-volt filament, even though this here is a 12AU6. It has a center tap on the filament winding, so it can run as dual 6-volt filaments. Anyway, this is the, getting in the shot again, this is the terminal that's used to feed in the 6-volt filament voltage. And the way I'm going to do it on the board, here it is right here, is I'm actually going to lay out the filament windings on the top of the board and run them through the cooling holes. These are holes I put in to allow airflow to come up through beside the tubes and actually act to cool the chassis and the components inside. Anyway, the wiring will come up through the holes, or down through the holes rather, to the tubes right at the point where they need to be to hook up to the tube filaments. And the plan here is to try and reduce 60 Hertz hum from the filament wires and prevent or minimize the interaction between that and the actual point-to-point audio circuit on the other side. And I'm paying particular care to this because the intention of the amplifier is to work with the low frequency range, of which 60 hertz and 120 hertz is right in smack in the middle of that. So trying to get rid of AC hum is a really big deal in this circuit design. Next up, we have the differential amplifier, which is this circuit here, and that is using a 12AU6 tube set up as a long trail pair or a differential amp. And this is a more clear diagram of it, and this is how I designed the circuit. The circuit's kind of unique in that it has a constant current source on the cathode side. And this guarantees that the source, the current being shared between the two triodes is always the same amount. So the sum of the currents going through each of the triodes is equal to the constant current source. In this case, the current source here is 5 milliamps. So on a balanced setup where both sides are using the same current, the current going through the tubes is 2.5 milliamps. So going back to the circuit, we have a shared current source here, 5 milliamps, and in a balanced state, each of these legs should be pulling 2.5 milliamps through them. When you go to the chart, you can map out the 2.5 milliamp current line, and then if we use a -5 volt gate to cathode bias, we can see that we can set our operating point or plate voltage to about 130 volts. That's where we want to see it be in the middle of this point. And as we increase and decrease the gate, or the grid, the first grid voltage, the cathode bias, we can move that plate voltage up and down along this line. So we get a fairly linear response that way by fixing the current. Of course, it doesn't work that way because, I mean, when you're increasing and decreasing the plate bias, the grid bias, you'll actually be changing the current going through the tube, so that actually the tube does move up and down in terms of current bias as well. So it tends to be more of a complicated relationship than just fixing the current. But I use this as a point to sort of figure out where I want to see my plate voltage for the quiet point in the tube where there's no signal being generated in the tube. So from that, I create a prototype, and this is a breadboard, and I actually have a tube socket here mounted on this, and that allows me to plug a tube in and actually hook it into the breadboard. So this is the current reference here. So that's actually using a linear regulator, an LM317, as a constant current source. And if you go to the data sheet on an LM317, you can see how to do that by using a reference resistor. I think I have the circuit here. So this is the circuit for constant current source. It uses R1 to adjust the current source and using a formula. I haven't got the formula down here, but it's easy enough to find. So where will this go? This will be this tube here. So this is the long-tailed pair, or the phase inverter, or whatever you want to call it. And that will be sitting in the middle between the two output pairs of output tubes. For the low voltage power supply, that's this thing here. I didn't really create a prototype, I just went straight to a PC board, and the result is this board here. It's a fairly simple design. I'm using a Hammond transformer here. This is an older one. I don't think they sell them anymore. This is a 161E16. There is a similar winding for a newer model, but it's, I think, essentially the same thing. It's just two secondaries as shown here. And I just use full bridge rectifiers on both of those. And then this board is essentially the circuit up to this point here. And the rest of the circuit is on the preamp board. So we'll go to the preamp board next. So I think I discussed this a bit in the previous video. We can maybe spend a couple more videos on discussing how, for example, the bass boost cut circuit works. Although, if you're familiar with doing active pass filters, it should be a pretty familiar design to you. This is a fairly, I wouldn't say famous, but it's a commonly used circuit for doing low pass and high pass boost cut circuits. The design was prototyped on a breadboard. Here's the input here, and I'm just using TL074s, which is a quad op amp, and a TL071 here, or an 072, which is a dual. I don't remember which one is this one. I think it's a TL071. This chip here is not on the final board. This is actually my amplifier. I'm believe using an LM386 here. Yeah, 386. It's just a single rail audio power amp, very low wattage, and I use that to actually drive a speaker so I can determine the frequency characteristics of this. This adjusts the gain that would go to the phase splitter, and this is my I think that this is the boost cut. Yeah, so I have a fixed gain on this. The circuit here doesn't show it. The actual final circuit, I did adjust it, and I put a volume control or an attenuator on the front here, and I have my boost cut in the final circuit, and then I have another trim pot here that just trims off the gain of the final stage before it hits the phase inverter, so I can actually get a good signal level and adjust it that way. So the prototype was tested. I might throw a short clip in here showing it working. We'll see. It's not that impressive. The design went to a schematic and then a PC board, and then I just had this PC board made. So the PC board is a design made and manufactured by Osh Park. I think they're out of Oregon. They're not. I decided to go with a North American one rather than a Chinese one. Chinese deliveries can be very variable in Canada, so it's it seemed like a better idea. This was a 5-day turnaround, and it was very quick, so it was very reliable, I guess you could say, in terms of delivery times. And the boards are fine. They're just standard tin HASL finish. They worked out fine. It's a mixture of surface mount and through hole. I put the op amps on sockets and using dip packages, so if any of them ever blow, it's easy enough fix to just take it out and replace it. This part here is actually not part of the amplifier. This is the virtual ground biasing for the 6-volt heater. So using this trim pot, I can actually try and reduce the 60 Hertz hum coming from the filament voltage by changing the point at which the virtual ground point is tapped onto the transformer. The transformer does actually have a physical ground on the 6-volt output for the filament heater. I'm going to play around with trying to use a virtual ground just so I can actually trim it and get a little bit more fine control over it, because it's not always right in the middle. It may be a little bit high or a little bit low depending on other parameters or operational characteristics of the amplifier. So this would be the volume control, and this is my bass, boost and cut, and it has a notch there so you can center it out at the midpoint. There's no treble on this, of course, because it's essentially it's a tube subwoofer amp, I guess, for the better term. So what's left to do? Well, I guess really the last part to do is to wire up this part here. I'm ready to go. I just left this because I wanted to show off the board without all the point-to-point wiring on it. I couldn't resist putting the ground bus on, so I did that as a quick one. I like using the ground bus bars because it gives you a really nice star point grounding scheme. And as an added bonus, if I need to tie off a component to ground, well, I've got a nice big long wire here. I can actually just wire in the component and tie it directly into the bus bar here instead of actually using up or trying to find an available terminal point. And it makes for a nice quiet amplifier design. This will be going to the main power board, and that will actually be the source of the star point for the entire grounding of the amplifier. For example, all of the coaxial cable will be grounded to that same point to minimize ground loops. So I guess by the next video, I'll have that point-to-point wiring done. I may have the board ready to power up and test, depending on time. I think things will get picked up a little bit faster, and I'll get more videos out as we get into the winter, because there's a couple of other things I want to do. There's a restoration project, and I also want to start leaning the channel in a new direction. So maybe this is a good point to start talking about where we want to go with the channel. The intention of the channel was always to have little vignettes or little pictures or little stories on the subject of engineering. And I kind of focused initially on TubeTech because it was something that is of an interest to a fairly strong but small audience of people that are interested in that era of technology. That's not my main focus in my career. I tend to be in a completely different direction, and I'm doing stuff more along the lines of cellular front haul. So it's absolutely nothing to do with what I do as a career. As an aside, I'm actually a firmware engineer, and I work with more embedded devices. So I'd like to sort of start doing some videos on that subject to start. So I'm playing around with maybe having an introduction to microcontrollers or something like that. Maybe we can play around with an STM32, which is a type of 32-bit ARM microcontroller. I can show you how to just get started in it. I guess you could think of it as kind of like what to do when you've outgrown Arduino sort of topic, because there comes a point when you're playing around with Arduinos when you realize you really need to get more out of this thing than you can get with Arduino. There's limitations to Arduino. I think they're improving it now. They have the ability to run multi-threaded Arduino projects, and they've outgrown the older 8-bit processors and they've moved on to the faster 32-bit ARMs. But believe me, you can get a lot more out of an ARM if you just move to a different framework and don't use Arduino, because Arduino actually does a lot of hand holding for you, and that does take up a lot of processor cycles. So we can take a look at that. I might play around with another couple of advanced projects, or viewpoints or vignettes. We may take a look at maybe doing some FPGA design work, maybe some Linux software. Embedded Linux is another topic that's vast and complicated, but we'll see. I mean, I'll come up with different topics and subjects and kind of come up with something to show during the winter. We won't forget TubeTech. We'll be coming back to it occasionally. I've got a couple of radios I can fix, but it gets a little monotonous. I mean, to me, I don't want to have the channel just focused on just that one topic, because I think there's more to engineering than just tubes. So anyway, I hope everything is going well with everybody in these times, and I'm wishing everybody well, and I'll just sign off now. Take care all.